Right, okay, so we're continuing on with the magnetism thingy me bobby. Right, we know, just say, for example, that's a magnet. That is the north and the south. We know, right, from what we've done so far, magnetic field goes from north to south. We know that. And if, right, this should not cross over, that's a bit poor, that. Right, and then I do one at that end, so they must not cross over, right? It always goes from north to south. So look, can you see it's traveling in that direction? So I know this is the north and this is the south. Right. The bar magnets are made from steel. Give one reason why steel is a good material for making bar magnets. So remember we said, so steel is a hard magnetic field. Oh my God. Did I just put that? I can't believe I did that. That's so silly. Magnetic material, not field. Right. You have, so that means that they stay magnetized longer. You also have something called a soft magnetic material. They stay magnetized very short periods, almost whilst the current's running through them. Oh, and not the current's running through them, sorry, the magnetic fields cutting across them. They'll magnetize. You could also put steel is hard to demagnetize, but I think this is the best answer by the looks of it. Explain how diagram 1 shows a magnetic field. So there's 2 marks. So first of all, these are parallel. And secondly, they're the same distance apart, the uniform, yeah? That's what makes it uniform. So uniform means consistently the same, if you can use those words. So the first of all, the field, magnetic field lines are straight. This is what you've got to do. You've just literally got to learn it dot for dot. The field lines are evenly spaced. And third, the field lines are parallel. There you go. Right. That's it. So remember there's 3 parts. The parallel, the straight, and they are evenly spaced. The diagram shows a metal wire being moved downwards. Right, okay. The orientation of the magnets has not been changed. So you've got north and south. Give a reason why a voltage is induced between the ends of the metal wire as it moves between the poles of the bar magnets. Right, so we know there's a magnetic field going across there. When a wire cuts a magnetic field, a voltage is induced. Right, this is because the wire cuts the magnetic field lines. When a wire cuts magnetic field lines, you get an induced voltage. A voltage is runs through it. Right. State that 2 changes that could be made that would increase the magnitude of the induced voltage. So how can you increase the... Right, so increase. The last question was decrease, so this is now increase. So if you're watching it in order, you'll understand what that means. It's in the previous slide. Let's look. Can you see this here? It says decreased. So you make everything weaker, right? Now here you do the opposite, right? So you can move the magnets closer. You can move the wire faster. Move the wire through the magnetic field faster. That will induce a bigger voltage. You can use stronger magnets. Yeah, I would use stronger magnets and cut the all right, okay, and they've also said use or turn the wire into a coil. That's cool. Right, so you've got that, you've got that, and you've got that. That's fine. Right. Yep, let's try this one then. The diagram shows some equipment from 1820. Yesterday, right? You've got 8 compass needles, so here, well, they're all pointing in a certain direction. Earth's magnetic field, right? Now, so that has no current going through it. So there's no magnetic field being produced, yeah? So you've got to remember that. Now, when you put a current through this, you get a magnetic field, some sort of magnetic field produced. Explain why the compass needles turn when the current is switched on. Right. No, it doesn't like it. Oh, it doesn't like it. It doesn't matter. We'll get over that. So the current through the wire creates a magnetic field. Right. The magnets in a magnetic field experience a force so line up along a field line. So what will happen is they won't line up in that direction, because that's where you get the biggest force. In this case it'll turn that way, and it'll line up with the least amount of force on it. Right, okay. What else was there? That's it. So the current through the wire create one word, right? Okay. 1 second. Causing trouble again. So let's try that again. So the current creates a magnetic field, and the magnets in the little compass will experience a force. Well, it'll generate a force on the needle, and that it wants to minimize the force, so it will line up along the field line. That's it. Just remember it that way. So the current generates a magnetic field. The magnets in the compass will feel a force, and they'll line up along the field lines. Right. Using evidence from the compass needles, draw on diagram 2 the shape and direction of the magnetic field produced. Right. Right, so I can let me get rid of that. That was my own version. Right, so what they want you to do is ideally draw a circle, one of the field lines, going through all of them. Right, I'm not going to complicate it. So it's going to go anti-clockwise. So it's got to be a circle. So that line has to be a circle in shape, and the arrow is going oh, not anti-clockwise, Control Z. Right, okay, 1 second. I pointed that in the wrong direction. It should be going, oh dear. It's all falling to bits now. Right, let me do it in green. So that's the direction of the magnetic field. In the wire. Right, okay, that's it. So we're assuming, what are we assuming? The current is going into the page. The current is going into the page. Yeah. So it's going down into the page. And if you use the right hand rule and wrap your fingers around, where's the right hand rule? Not that one. Not that one. This one here. Hello, hello, hello. It doesn't like to behave today. I don't know why it's not behaving. Nope, we don't want to behave. Right, okay. So we've got to assume it's going into the page, and when we wrap our fingers around it, it's going clockwise. Right, leave it at that. Let's move on. Suggest what happens to the magnetic field when the current in the wire is reversed. Right. The magnetic field will change direction. Right, okay. The current in the wire is turned off. The current in the wire is turned off. Diagram 3 shows the wire placed in a uniform magnetic field. So, right, that's time for me to go. So let's get this part finished. So it's going from north to south. Right. Right. The current is now switched on, so we use Fleming's left-hand rule. So remember we said we said what did we say? We said thumb is mother, first finger is father, third finger is child, so that's motion, that is field, and this is the current. So what we do is, let's do this. I might have to finish this off later. So that's your first finger, that's your current first finger, sorry, second finger, the child, right? The field is your first finger, it's going that way, right? And the current's going that way, the first finger's going that way, the thumb will go in that direction. So if you hold your finger, yeah, let me take another picture. It's let me take the picture. Hopefully you can see that. Right. So let's try that now, yeah. Let's try that. So here's your current. There's your current. Your field first finger goes that way. It's running across there, so there. And then that leaves, because it's on the left hand, that leaves the thumb pointing upwards. So the motion will be upwards. So that wire will flick up. I think that's the way it goes. So we're draw an arrow to show the direction of the force, so it will be up. So draw an arrow. So we'll just draw a vertical line upwards. So what color can we use? I don't know what color. It will be blue. So it'll be going upwards that way. Right. The power supply in diagram 2 is replaced by an ammeter. When the wire is moved, a current is detected. Explain which direction the wire moves in the direction the wire is moved in the magnetic field to produce a current in the wire. Oh, when a wire is moved, a current is detected. What they replace? Okay, so they've replaced this with an ammeter just to measure the current. Right. So what happens is you have to move the wire up and down here to cut across these field lines. So you move it up and down to cut magnetic field lines. That's it. Explain why a current is produced in the wire when the wire is moved in the magnetic field. It's to do with induced voltage. So when a wire cuts magnetic field lines, a voltage is induced. As voltage is induced, right? They've put across the wire. Right. And the circuit is complete. What does it mean? Let's take let's take that. So you've got an ammeter here, This circuit here is one complete circuit. So then that means that the current can flow. So the circuit's complete. So a current flows. These are the 2 points that they want you to have. Right, that's good that. Right, that's that done. It was a bit strange, but it's done. And hopefully the others will become, oh, 1, 2, few more questions coming up. Right, okay, that's good. I think the more questions we get, the better we'll become, the stronger we become at it. Right, so that's our next question. We'll call it quits here.